Our plant uses renewable biomass like palm shells and rice husks to generate clean electricity. The system works on a closed-loop Rankine cycle, converting heat from biomass into steam to drive a turbine. Key components include the boiler, turbine, generator, cooling tower, and flue gas treatment units. Our objectives include designing a biomass-based power plant and creating a process flow diagram in AutoCAD. We explain the system using the Rankine cycle, calculate its thermal efficiency, compare with two other power systems, and include pollution control units like the economizers, cyclone, and ID fan.
So I'm here to present our proposed biomass power generation plant design, capable of producing up to 100 megawatt using renewable biomass fuel. The plant operates based on a closed-loop Rankine cycle and is engineered for both efficiency and sustainability. We begin at the biomass storage tank, where solid biomass such as palm shell, rice husks, or wood chips is stored. From there, a screw conveyor continuously feeds the fuel into the boiler. The mechanical feeder is critical for steady combustion and prevents backflow of fire or gases. Inside the steam boiler, the biomass is combusted, converting water into high-pressure steam at 311 Celsius and 15 megapascal. The hot flue gases pass through an economizer, where they preheat feed water, improving the plant's overall efficiency. The gases then move to a cyclone separator and electrostatic precipitator, which is ESP. These two units remove solid ash and dust particles, minimizing air pollution and protecting the chimney system. Clean gas are then drawn out by an induced fan and expelled through the chimney. The high-pressure steam flows into the turbine, expanding the spinning the shaft, which drives the generator to produce electricity. The output electricity is sent to a step-up transformer and transmitted via cables to the power grid and consumers. After doing work in the turbine, the steam exits at around 800 Celsius and 10 megapascal and enters a condenser. Here it's cooled down by water from the cooling tower, turning the steam back into liquid. This condensed water is pumped by a centrifugal pump back into the feed water line, completing the Rankine cycle. The water is now directed back through the valve before re-entering the boiler. The plant uses a closed-loop cycle, minimizing water loss. An external feed water tank is only used for system startup and backup water.
Our plant uses reliable, high-performance equipment to convert biomass into electricity efficiently, then cools and recycles steam through a closed Rankine cycle.
Next, we will move to the calculation. To solve this calculation, we will use the Rankine cycle, and there are some things to take into consideration, such as pump and turbine are both isentropic. There are no pressure drop in boiler and condenser. Stream leaves condenser is a saturated liquid. And assumptions that are made are heat going in and heat going out are both equal to 0, as well as work going in and work going out are also both equals to 0. In step 1, we assume that it is a saturated liquid. Therefore, the value of pressure is 50 kilopascal. The temperature is 81.32 Celsius, and we can obtain the value of temperature, specific volume, enthalpy, and entropy from the table A5. We know that the pressure in state 1 is equals to state 4, and state 4 is a saturated liquid vapor mixture. In order to find the value of enthalpy, we have to find the quality for state 4, and we can find the value of quality by using table A5. State 2, we know that it is a compressed liquid, therefore the pressure is 10,000 kilopascal and the temperature is 311 Celsius. We can find the value of specific volume, enthalpy, and entropy from table A7 by using interpolation. And for stage 3, we know that stage 3 pressure is equals to state 2 pressure, and it is a superheated vapor because the temperature in state 3 is higher than the T set from table A7. And we can obtain the value of specific volume, enthalpy, and entropy by using table A6. Next, in my slide, I will show you the calculation step one by one. In order to find the specific enthalpy for state 2, we have to use the formula of W pump in equals to H2 minus H1 equals to V1 times P2 minus P1. Therefore, the value of specific enthalpy in state 2 is 350.7885 kilojoule per kilogram. In order to find the quality of state 4, like I said, we have to use the value in table A7, and the value of quality for state 4 will make us find the specific enthalpy for state 4, which is 2576.099 kilojoule per kilogram. In order to find the efficiency of the process, we have to use the formula, which is efficiency equals to work net divided by heat going in. We have to plug in all of the value of specific enthalpy, and we calculate, and then we get 0.41, which is also equals to 41%. So in our calculation, we can conclude that heat going in is equals to 3,763.71 kilojoule per kilogram. The heat going out is 2,235.550 kilojoule per kilogram. The work net is 1,528.151 kilojoule per kilogram. The efficiency is 0.41, and the capacity of power were found by multiplying the mass of biomass produced per year, the W net, the efficiency of boiler, the efficiency of generation, which all equals to 1,680.2158 megawatt.
And now we are moving to the part of comparison, to compare between our plant power generation systems and other two systems, and that in terms of thermal efficiency, capacity, fuel sources, environmental impact, and other points. For the capacity, as you can see, for our plant, the capacity is around 1,680 megawatt. And for DIMA power plant, the net output is around 1,400 megawatt. While for CATL solar power generation system, so once it use the photovoltaic effect and not use heat, so the typical container CATL thinner stack offers around 9 megawatt per hour per 20-foot container, and utility scale projects can range from tens to hundreds of megawatt per hour or gigawatt per hour by deploying multiple units. And for thermal efficiency, for our plant, as it is calculated before, our thermal efficiency is about 41%. For DIMA power plant, it is around 55.9%, and for CATL is a range between 15 and 22%. In terms of the process cycle for our plant, it is a Rankine cycle, and it converts biomass into steam to drive a turbine. And for DIMA power plant, it has Rankine cycle and also Brayton cycle. For CATL, as it is electrochemical process, so it has charging and discharging. For charging, it converts the electrical energy to chemical energy, and the opposite in the discharging by converting the chemical energy to electrical energy, and at the same time no combustion or mechanical work. For the equipments, for our plant we have biomass storage and screw feeder, steam boiler, steam turbine and generator, flue gas handling, which is economizer, cyclone, ESP and others. We have also cooling tower and condenser, feed water pump and etc. So for DIMA power plant, it has boiler, steam turbine, generator, cool continuous unloader, stacker reclaimer, electrostatic flue gas, low NOx burner. For CATL, it is a solar panel, inverter, load and grid, TMB grid system, and bi-direction. For the fuel sources, our plant uses renewable biomass fuels such as palm shells or rice husks to generate clean and sustainable electricity. And for DIMA power plant, the main fuel is coal, and the annual coal consumption is about 4.3 megaton. For CATL solar power generation system, no fuel consumed in operation, so it stores electricity from other generation sources. Regarding the environmental impact, our plant helps reduce dependence on fossil fuels and supports environmental protection by converting organic waste into energy. For DIMA, our power plant is fully committed to adhere to all of its environmental compliance obligations in all its activities and business process. For CATL, the environmental impact is low during operation and moderate to high during the manufacturing and end-of-life phases.
In short, our biomass plant is clean, efficient, and built for a greener, more sustainable future.